Okay, got it. So let us continue. So we were discussing properties of quantum cohomology and quantum products. Last proposition was that if I pick two elements in complexified cohomology theory of a variety X, which are homogeneous, then they can be written in terms of homogeneous generators with this degree condition, that the degree is degree of A plus B modulo 2. Okay, so we proved this thing. Let us continue now. Here's a proposition. For any A and B and C in complexified cohomology of our variety, we have the following property. So first of all, if I apply, this is the intersection matrix. If I take A star B, this is the quantum product, right? So this is quantum product of A and B. A and B are two cycles. We have discussed it. The quantum product of these two things basically is that this is A, this is B, and it's a sum of all possible curves that have some incidence with A or pass through A, and they have markings that pass through B. Okay, and then for that you need a third point, and so this third point P1, because we are doing a small quantum cohomology, so the curve, genus zero curve, needs to have at least, if it's a non-constant curve, it needs to, if it's a constant curve, it needs to have 3 at least mark points. So it needs to have stability, and the third point needs to lie on some cycle. And that cycle is the cycle we called TI. It's a generator of homology theory of the ambient variety. So as you vary over possible TIs, it could be that P2 is matched with a point. It could be that P2 lies on a line. It could be that P2 lies on a surface. So these TIs are Poincare dual of homology class of all these possible things, and they generate the homology. So we need this TI, and the sum we get is sum over TI. So that defines the A star product B, and then G, on the other hand, is so that A star product B is a homology or cohomology class, and I can take its intersection with the third cohomology class, okay? And the statement of the theorem is that this condition is satisfied, basically, and this is going to be equal to summing over all beta in integral homology of X of I0 3 beta of A, B, C. Okay, and then you need some variable that keeps track of beta, and we have defined what this variable means. This by definition was e to the 2 pi I integral of the Kähler class of the variety against beta. This is that power of Q is. It depends on beta, so we can call it beta, but it's really a number depending on it. Okay, so that's that. So this statement is actually compatibility between quantum product and usual intersection product. This is the usual intersection product between any two cycles. Okay, so this is that. And the part 2 of this proposition is that we would like integral of the quantum product between A and B be equal to intersection product between A and B over X. Okay, all right. So proof is, here's the proof. I'm just sketching it. It is easy to show that G of Ti star Tj, these are the generators of cohomology, with the third cycle Tk is equal to summing over all beta of I03 beta of Ti Tj Tk q to the beta. Okay, so using, this is something that we have seen before, and using supercommutativity, we also saw that the star product or the quantum product is supercommutative. Commutativity, it is easy to see that if I take G of T I, Tj star Tk, if I move it over, it's going to be -1 to the degree of Ti times degree of Tj plus degree of Tk times G of Tj star Tk Ti. So this is how, if you move this over here and move this over there, it's a supercommutative thing, product. Therefore, and since G of Ti star product Tk and Ti is the sum of I03 beta Tj and then Tk and then Ti by what we showed before. If we get to the beta, sum is over beta, okay? We will get part 1. We'll get part 1. Okay, and so this, by the way, this we will get part 1 from equivariance axiom. So we know that Gromov-Witten classes are equivariant with respect to the mutation group, the symmetric group that mutates the cycles, equivariance. Now for part 2, if I take integrate quantum product of A and B over X, that will be the same as integrating, copying basically fundamental class of X with A cross B. Okay? But that's exactly, again, by what we have seen before, is G of T0 and A cross B, which is equal to G of T0 cross A and B, because we know that this quantum product is associative. We proved it last time, and this is G of A comma B. Okay, so this is by associativity. Associativity of quantum product. Yeah, okay. All right, so here, what is this implication of this thing? So the remark is the following. This implies that the cohomology, complexified cohomology ring of a variety is a Frobenius algebra under star and G. What's the Frobenius algebra? Frobenius algebra is an algebra with 2 notions of product on it, and exactly the compatibility relation that we have in here. That's exactly what it is. This Frobenius, okay, so let me, what does that mean? It means that it is commutative, associative algebra with a unit. We do have a unit. This is the fundamental class of ambient variety, together with a non-degenerate inner product structure. So inner product blank blank, yes, on so this inner product for us is the intersection product, right, on this ring, so this I would like to be my ring under the quantum product, okay? And I want this satisfying exactly G of A cross B and C equal to G of A, B cross C, or else A cross B, C, I want it to be A and B cross C, same thing. The products being intersection product, okay? So this is a very important result because under these two, the cohomology theory of X with complex coefficients is going to be a Frobenius manifold. Second remark 2, is that we can relate the 3-point, relate the 3-point function that we had before to quantum product. And it's exactly because of this statement that I just proved right here. Okay, the 3-point function, so this was it. So if you give me 3 cycles, this was the 3-point function. 3-point function was the Gromov-Witten invariant made of 3 cycles, and it is actually was defined as sum of I0, 3 beta Gromov-Witten classes passing through the 3 cycles, Gromov-Witten class of curves passing through 3 cycles, and then coupled with the coefficient that keeps track of the curve class. Yeah, so the quantum product is actually giving us cohomology class, but the function, the 3-point function or n-point function, in some sense is really counting for us how many curves pass through those many cycles, right? It's the integral of the Gromov-Witten class for different choices of curves, curve homology classes. And we can see that and see that A cross B, which lies in here, is the unique element, is the unique element satisfying, well, G of A cross B with C intersection is exactly the quantum 3-point function for any C in complexified cohomology of the variety. So what does this definition imply? This definition also implies that A cross B is the sum over I of A, B, this is another way of writing it, A, B, and Ti. A, B, Ti, Ti, where Ti's are the generators of homology. Okay. So if you accept this, moreover, the 3-point function of ABC can also be written as an integral of star product of ABC. So this is the small quantum product. All of them, everything that we have been doing so far is a small quantum product. Okay. So yeah, so that's what it is. So it is very important to note that all of these constructions depend on the definition of Gromov-Witten classes and the definition in particular of Gromov-Witten invariants. So as we have NO here, with NO we are discussing about super Gromov-Witten invariants, and you must understand that super cohomology classes are not really well defined. But hope is to define super Gromov-Witten invariants and define these products. So the product is written in terms of Gromov-Witten invariants anyway. So it might be that I cannot define super cohomology, but I might be able to define super Gromov-Witten invariant. Okay, so that's kind of the remedy to it. So, okay, so here is an example. Let us think that X is the projective space, PR. Use the cohomology. So we know that projective spaces have cohomology theory generated by hyperplane class. Use the cohomology basis H to the I, that means cup product of hyperplane class with itself I times, like that, where H is the hyperplane class. H is the hyperplane class, and exponent refers to the cup product, right? So if you take hyperplane class intersected with itself R times, you get point class. Okay, so here's what we claim. We claim that HI quantum product with HJ is either HI plus J if I plus J is less than R, okay, or it is Q times H I plus J minus R minus 1 if I plus J is bigger than R plus 1. Okay, where Q is e to the 2 pi I again, integral of W against L, and L inside PR is a line. So this is an element of H2, and okay, e to the, so I don't like this, oops, let's make it a small, e to the whole thing. All right. Okay, so here's the proof, how you prove this statement. Proof is that let beta to be the class of degree D genus 0 curves, which has D times class of a line. So D is bigger than 0. Then by degree axiom, which restricts the degrees of the cohomology classes, we can play with cohomology classes all generated by hyperplane class. We can see that I 0, 3, D times class of the line of HI, and then HJ, HK is equal to 0 unless, we have proved this thing before, I plus J plus K is equal to R plus D times R plus 1, unless this condition is satisfied. This is the restriction that we have on sum of IJK, because that's the expected dimension of the, or expected degree of the Gromov-Witten class, which is the expected dimension of the moduli space of curves. So since I and J and K are less than R, then what does that imply? Either D is equal to 0 or 1, and D equal to 0 if D is equal to 0 if quantum product of HI times HJ is equal to HI plus J when I plus J is less than or equal to R. So in particular, when I is itself less than R and bigger than 0, then this HI would be the same for cup product and a small quantum product. So HI will be the same for cup product and small quantum product. If so take quantum product of HI with itself many times, when I is less than R, it will be the same as the intersection product of HI with itself, so and a small quantum. This is a fact. So to finish the proof, it suffices to show that H star product with H R is Q to the H0, right? And in this case, actually, D is equal to 1, and we had Hij, K is equal to R here, right? So that's the only thing. So in that case, H star HR is equal to, by formula, just follow the definition, 0, 1 times class of the line, right? And then we have H itself, and then H to the R, and then H to the R, QH0, right? However, if this is the case, remember that if I take intersection of H with itself R times in an R dimensional variety, I will get the point class. So this is the class of a point, and this is also a class of a point. Okay, so this is the same as I03 line H point and point. Point and point. Okay, that's good. Now I'm so I'm counting curves of genus 0 passing through ambient, going through ambient variety, embedded with 2 points that lie on a line. Well, okay, as soon as you give me 2 points of that line, that fixes my choices. That it's only one line that passes through, so that's just equal to 1. This number is equal to 1 because the 2 points determine a unique line, right? Which meets, by the way, meeting H at the third point. At a third point. So the third mark point is the one that needs to have incidence with this hyperplane inside ambient variety. So this finishes the proof. Okay, so this is one example. Then, by the way, another thing, so another remark is the following. It's based on degree axiom. So we know that the 3-point function is basically this here, right? So corollary of this thing, is that for a Calabi-Yau manifold, X, the quantum product satisfies based on degree axiom, it satisfies that degree of A cross A star B is equal to degree of A plus degree of B. And moreover, if A is cycle in HPQ of X, like that, yes, and B is a cycle in HRS of X, these are complexified, right? Then A star B is a cycle in HP plus R and Q plus S of X. Mahaj decomposition. So how do we see that? To see the proof of one, this follows from a proposition. So this follows proof. So this follows from our proposition that we know that degree of A plus degree of B is equal to degree of the Tj, so it's by the degree axiom, minus 2 times integration of Kähler form against the curve class beta. But the Kähler form of the ambient variety is equal to O. So when you integrate this against beta, it's basically measures the degree of this line bundle against that curve, the points of intersection, and that's equal to 0. Right? So this is something that we had before, right? I mean, this is the one that we had. Degree of C is degree of A plus degree of B modulo 2, when CL C is equal to A cross B. So this is the thing that this follows from that proposition. Okay. So part 2 is the following. So if it is Calabi-Yau, it's much easier. Degree of A plus degree of B, because that even part just goes away. Now part 2, suppose X has dimension, for instance, n, then it suffices to show that we would like to show, okay, so it suffices to show that the Gromov-Witten number of the 3-point function that we define this way is going to be 0 if C is not an element of n minus P minus R and the n minus Q minus S, right? Because basically this is what we are trying to prove, right? So this follows by the fact that G of A cross B and C is compatibility between intersection product and quantum product. This is equal to summing of I03 beta ABC Q to the beta. This follows from that. Okay. However, since M bar 03 is a point, this is a 3-point function, we know that in fact I03 beta of ABC is nothing but A tensor B tensor C integrated over pi 1 over star of the virtual class M bar 03 beta of X. And this is pi 1 is the map that takes us from M bar 03. Okay, so actually I'm using a bad notation, maybe X and beta, like that, to X cubed, the evaluation map. Evaluation map. Okay. Now, on the other hand, we need to see what is this algebraic cycle that we are evaluating on X. So since M bar 0, 3, X and beta is an algebraic cycle, of expected dimension, This is by construction. We discussed about construction of this cycle a lot, previous sessions. So it has this expected dimension exactly. Yes. Then one sees that pi 1 lower star of M bar 0, 3 of X beta, the virtual class, right? It's gonna be in H2n of X cubed, which is in H2n of X cubed, is cohomology class of an algebraic cycle. So not only itself is an algebraic cycle, its push forward is an algebraic cycle sitting exactly here, right? And then from here, it is immediately seen that integral of A cross B cross C over push forward of this algebraic cycle is going to be 0 unless the degree of A times B times C, so this thing has degree equal to degree of the cycle, and that's degree nn. Because of that, that means this statement. That means that this class C needs to complement basically, where was it? So this implies exactly here. So that means that the tensor product of A and B needs to have class P plus R and Q plus S. So that's simple. Okay. All right. So that's just 2 remarks and 1 example over projective spaces. Okay. All right. So I think that we are going to, I'm not sure. So we will see, but probably we are getting closer and closer to kind of ending the section on Gromov-Witten theory and getting closer to Donaldson-Thomas theory, because the story of Donaldson-Thomas invariants started from Calabi-Yau varieties and still even over higher dimensional varieties like Calabi-Yau fourfolds. Donaldson-Thomas invariant is only defined for Calabi-Yau, really. Then I think let's discuss about Calabi-Yau. So here is, to continue the discussion, small quantum cohomology of Calabi-Yau manifolds. Okay, so we discuss a little bit about this, and then we go to Donaldson-Thomas theory, which got their life from studying of shift theory on Calabi-Yau. Okay, so here is a lemma. If X is a smooth Calabi-Yau 3 manifold, then A quantum product B is equal to A intersected with B, A cup product with B, if neither, yeah, that's harder to say, if either degree of A is not equal to 2 or degree of B is not equal to 2. So here is the proof. Need to show that the Gromov-Witten invariant I03 beta of alpha 1, alpha 2, alpha 3 is going to be equal to 0 whenever beta is not equal to 0. You're counting holomorphic curves, and degree of alpha i's are not equal to 2. So how do you prove this statement? By degree axiom. I mean, this degree axiom is just has an incredible amount of applications. But degree axiom for this calculation of this invariant alpha 1, alpha 2, alpha 3, we can assume that some of the degrees of alpha i's is some 2n, right? Now, since either alpha I is fundamental class, if it is fundamental class, its degree is 0, right? Either it is a fundamental class, which means its degree in cohomology is equal to 0, or it's not, or alpha I is the class of some subspace, in which case, because we are calculating real degree, or degree of alpha I is going to be bigger than or equal to 2, right? If it is a divisor, it's 2. If it is codimension 2, it's 4, so on and so forth. Therefore, there are two cases to consider. So there are two cases to consider. Yes. So one case to consider is that one of these alpha i's, so one of alpha i's is a fundamental class, is the fundamental class of the variety. That's one case. Two is degree of alpha I is equal to 2 for any I. Okay, so the first part is by fundamental class axiom, equivariance axiom. I'm not going to write it because you can follow the argument, equivariance axiom and point mapping axiom. You can actually see that we can see that the corresponding Gromov-Witten invariants are intersection numbers or 0. Okay, for part 2, if that's the assumption, if the degrees of all of them are 2, that means all of them are divisor classes, then we use the divisor axiom. So the divisor axiom gives the following. So I0 n beta of alpha 1 to alpha n is n of beta integral of alpha 1 times all the way integral of alpha n. right? And then this is going to be if beta is not equal to 0, if this is the case, if beta is not equal to 0, and if beta is equal to 0, okay, then it means that because I'm looking at divisor classes, so if beta is equal to 0, it means that image of the curve into the ambient variety is just a point. So Gromov-Witten number should be, Gromov-Witten class should be class of, basically cohomology class of the locus in the ambient variety where all alpha i's intersect with each other. That's the only way. That point needs to lie on all of the cycles, right? But if it is a pointed map, that means all of those cycles need to meet exactly at that point. So, well, okay, how is that going to be achieved? So then, otherwise, if beta is equal to 0, this is what happens. Then I have I0, N0, right? Alpha 1 to alpha n. But this is, we also saw this before. So this is alpha 1, alpha 2, alpha 3 intersected in X if n is equal to 3, otherwise it's 0. Yes? So basically, that's what it is. So that's kind of, you know, almost proves this. Okay, so now, for instance, let us assume that X is a given Calabi-Yau threefold. So X is a quintic threefold in P4. We know that this is a Calabi-Yau. It remains to compute quantum product in H2. Yes. So in this case, because they are all divisor classes, in this case, the quantum product is uniquely determined by H quantum product H. That's the codimension 2. So where H is an element of H2 of XC as the hyperplane class. So basically, H star H lives inside H upper 4 in real dimension of this complexified cohomology of X, right? We also know that if I have H3 over X, it's 5. If I take the hyperplane class, intersected by itself, I recover the degree of X inside P4, and that's exactly degree 5. Hyperplane class of X, which is the ample bundle associated to the ample bundle, comes from pullback of hyperplane bundle in P4. Because the X has degree 5 in P4, if you pull that thing back and intersect it with itself 3 times, you'd recover degree of X. Right? So, okay, now I can calculate. So if I have H cross H, basically, this is going to be equal to 1 over 5, d from 0 to infinity of I03d, H comma H comma H. Q to the d times H2. And by here, I mean the degree d line. So, okay, so let me just see, by here, I mean d times class of a line, genus 0 curve. Okay. On the other hand, we also know that this 3-point function is the same as by what we just showed, quantum product of HHH, and this is also equal to I03D HHH Q to the D, Q to the D, right? So remember that this Q is e to the 2 pi I omega of x against beta, and keeps track of class of the curve, and the class of the curve is exactly d times class of that, right? You can also write Q to the DL, it's okay. This is a formal super index, really. So beta is equal to d times class. Okay. If you could do this computation, you can actually see H cross H, or H star H, is H, the 3-point function, times 1/5 H squared. Okay, so the quantum product is written in terms of 3-point function. This is a very important thing. Okay, so for arbitrary Calabi-Yau threefolds, it's very similar. So for arbitrary Calabi-Yau threes, also you can actually see that the quantum product can be written in terms of the 3-point function. So here, for instance, we have that if I have 3-point function like this, again, based on what we saw, this is the case, and this is given by I03 beta of ABC Q to the beta. But this, again, can have possibilities. Either my curve is, my cycle beta is 0 cycle, or it's something non-zero, but we are over the Calabi-Yau variety, and we have the constraints we have on the degree. So this is going to be either this thing, which we know how to calculate, that's the intersection product of these things, or the part for which beta is absolutely not equal to 0, I00 times beta, right? But this would be times by what we just showed, integral of A, integral of B against beta, and integral of C against beta, times Q to the beta. This is basically the statement that we had here, right here. Okay. So, okay, so these are examples that you can see. All right, what else can I say? Maybe a remark is the following. We did discuss this before, but maybe here is a remark. Coefficients in quantum product okay, so far we have used cohomology with C coefficients, right? We have seen that, for instance, Q to the beta, we defined it as e to the 2 pi I integral of omega against beta, and this is a complex number clearly. So this product that we are calculating over and over is going to be giving us a complex number times the cohomology class. So here is just a 3-point function, so it is literally a number. Okay. Where omega was in H2 of X with complex coefficients is the complexified Kähler class, is the complexified Kähler class. Kähler class. But we saw that this could be a problem, but the sum on the right side of A star B is not necessarily convergent, is not necessarily convergent. And we discussed this thing briefly before. We need to kind of use a formal sum, really. So what is the remedy? The remedy of this thing is to think of q to the beta itself as a formal variable, rather than a number. Okay. And if you remember, I actually showed that over homogeneous varieties, which have transitive action of a group, these convex varieties, by convexity, this sum converges. And over Fano varieties, also the sum converges, because we saw that over Fano varieties, the bigger and bigger curve classes I give in here, because omega is a negative anti-numerically effective line bundle, then we saw that this will be e to the minus some number, and it kind of diverges, it converges to zero. It kind of stochastic, asymptotically decays. So we get the finite sum. Yes. So, all right. So for Fano X, we saw that sum is finite. In this case, if I really want to think about my cohomology theory of X, I can add this formal variable to the ring of cohomology of X. So I can think of R to be a ring with rational coefficients, where I have added this formal variable, and then I have beta in H2 of XZ elements in it. So this is some kind of a newly souped up cohomology ring. Okay, and so this is a semi-ring, actually semi-group ring, which means that each beta which lies in H2 of XZ gives a formal symbol q to the beta, okay, such that if I take q to the beta 1 and take it, it's a formal variable, q to the beta 2, this should be q to the beta 1 plus beta 2. And an element in this semi-group ring, an element in R is a finite sum of q to the betas. Okay, with coefficients in q, with coefficients in Q. All right. An easy example is with the projective space itself. So an example of this thing, when X is equal to PR. Okay, if it is the projective space, its canonical bundle is O minus R minus 1. R is positive, so it's antinumerically defective. So it's funnel. So where we have that this semigroup ring, formal ring made of homology, ring of PR becomes it becomes Q of Q and Q minus 1. The ring of Laurent polynomials in this formal variable Q. In general, this is not the case because these sums are not finite, but for general projective variety, however, projective variety X, however, this R is, well, some kind of a power series in terms of this variable Q and beta in the, let's call it Mori cone of X, right? Mori cone of X. Okay, so this is just a remark. This is how you can actually see that when you use this formal variable, you can actually see that it solves this ambiguity of Q to the beta being an infinite sequence of numbers. So we just think of it as a generalize the cohomology ring of X with this formal variable. Okay, so I think that this is where I like to end the discussion on small quantum cohomology. We can discuss about big quantum cohomology, but before that, there is something that a lesson I would like to take out of this, which is, as you have seen so far, especially in this last example, you can see that when you calculate the quantum products, it turns out that the number of curves passing through certain number of cycles would be some number, but then you have coefficients, and those are rational numbers. So in some sense, the problem with Gromov-Witten invariance is that the machinery of it being intersection numbers on the moduli space of stable maps allows you to count them up to orders of automorphisms of those things. And if you calculate some number of curves passing through some given number of cycles, you obtain a rational number for that. You cannot necessarily enumeratively quantify how many curves are they after all. I mean, what is it if your number is 2/3, for instance? How many curves did pass through that many cycles? You cannot necessarily make a decision. Is it 2 curves with automorphism 3, or is it 4/6, or what is it? The problem with Gromov-Witten theory is this rationality of Gromov-Witten numbers. Even though it gives a lot of insight to us, it's still not compatible completely with the original idea in superstring theory that you have this Riemann surface and it's undergoing certain fluctuations and it's pinned in certain locations in the ambient variety to certain cycles, and you would like to count it. So the set of Gromov-Witten numbers are not enumerative, infinitely many Gromov-Witten numbers. As we saw, the difference between Gromov-Witten number and the Gromov-Witten class is that it's defined for any genus and any number of mark points. So it is true, in fact, that Gromov-Witten numbers are infinite sequences, but they are not enumerative. So following this ideas, it was a somehow very kind of, this issue triggered algebraic geometers to replace counting of curves in ambient varieties with a different perspective, meaning counting certain objects representing curves in the ambient variety, hoping that the numbers you calculate out of this counting are integers, so that they become enumerative. And that's the discussion of Donaldson-Thomas invariants. So let us start this discussion, but I will continue it in the following sections. So we're going to discuss Donaldson-Thomas invariants. By the way, the big quantum product, meaning higher genus curve counting, I will discuss it later. The reason I'm not doing it in here is that there is a long discussion about how to count a higher genus curve in an ambient variety. In so many cases, you can do that. In Calabi-Yau varieties, for instance, that's problematic, other than C3, I guess, which is toric Calabi-Yau, but in other ones, it's problematic. So very hard to calculate those things. So we will discuss it later. But for now, let us go to Donaldson-Thomas theory. Counting sheaves in ambient varieties. Okay, so you would like to have the ambient variety, and in Gromov-Witten theory, you are counting curves. For instance, if I have a curve in the ambient variety, then I would like to replace this picture with again ambient variety and some kind of a sheaf that is supported on ambient variety. It might be that the sheaf is supported everywhere. Sheaves are like bundles, but maybe with certain singularities. They are not locally free necessarily. So I would like to count these things, hoping that order of automorphisms of these sheaves is 1. So if I can make a relationship between curve counting and sheaf counting, then I can just use sheaves to count curves. And that's basically the focus that we are gonna have for a while, okay? So let us talk about these sheaves. So I'm going to discuss about ideal sheaves. Ideal sheaves. Okay, let us say that I fixed for now, because Donaldson-Thomas theory started from 3 folds, I fixed the complex dimension of the ambient variety to be equal to 3. Fix a curve class. Fix a class beta in integral homology of X. It's a curve class. And fix an integer. Fix an integer. I'm gonna cook up a sheaf which is very close to curve in X with class beta. Fix an integer. Let's call that integer chi, and it is element of Z. Okay. With this information, I would like to construct a space that parameterizes curves inside X with also possibility of deforming in X. Okay, so here's a definition. The Hilbert scheme Hilb of chi X comma beta, it's written like this, of one complex dimensional subschemes of X with numerical characteristics or invariance numerical characteristics beta, and chi parameterizes subschemes. So this is your X. It parameterizes subschemes. I'm gonna call this subscheme Z. Subscheme Z, subscheme of X, whose irreducible components are at most one-dimensional. Okay, such that if I look at the structure sheaf of the subscheme, pictorially, it looks like a holomorphic trivial bundle which is supported on the subscheme itself. That's what the structure sheaf looks like. Okay, so if I have that, and if I calculate Euler characteristic of this thing, this is the Euler char, it is equal to chi. And I would like the class of my subscheme Z to be the fixed curve class in the ambient integral homology of my variety. So this is the cycle class, cycle class of one-dimensional components of this Z, subscheme Z. Okay. Now, you might say, why is it that this is a curve? Why do I keep saying irreducible components are at most dimension one? I think that's obvious. But why do I say the cycle class of one-dimensional components of Z? What else can be there? The point is that when you look at sheaves associated to subschemes, they could have components, not all of which have the same dimension. So the issue in this picture is that if you have X, you can have a system of a curve, bunch of embedded points on the curve, and bunch of points off the curve, and the whole thing would be the subscheme Z for us. So this whole thing is Z inside X. If I just look at the curve part of it, only the curve itself, with the points removed, the embedded points removed, this is the pure part of the subscheme Z. And the embedded points are non-pure part of it. So these are embedded points. So you might say, well, I don't understand that. I don't understand what's going on. The point is that module theoretically, in algebraic geometry, subschemes are basically associated with sheaves, with ideal sheaves. That's what Zariski topology is all about. And so you can always think about ideals that can correspond not just to a naked curve, but some kind of curve together with some lower dimensional subschemes like these embedded points attached to it. Here is an example. Maybe this illustrates the issue for you. Consider the limit of two lines, two skew lines in P3. So what's this story? Let us look at P3 locally. P3 locally looks like C3. So I have locally in P3, I pick one of the affine patches. Right? P3 has 1, 0, 0 point, 0, 1, 0 point, right? And 0, 0, 1 point, right? It has these things. Okay. I pick one of these affine patches. And then around that affine patch, I can have these local axes. And I can look at the curve. I can look at some kind of a curve like that. So I am now locally in here looking at a copy of C3, looking at exactly those two skew branches of the curve. What do I see there? Let us assume that I choose my local charts in a way that one of the branches lies on my axis Y. And let us assume that the other branch lies on is a skew, as you can see. So these are the two branches of the curve. Okay. Now I want to do algebraic geometry. I would like to look at ideal or structure sheaf of this thing locally. Structure sheaf locally is a module. So we would like to write O of Z, this is my Z, subscript Z, locally, or module theoretically. Module theoretically. Okay. All right. So let's just see. Let us assume that we are looking a snapshot. So this curve is actually in the limit is deforming. And these two branches are kind of approaching one another. So let's say the height between these two things is some parameter t. So they are t steps apart from each other, t units apart from each other at this very moment that we are looking at. Okay, so that's not a problem, right? Because I can actually look at O of Z locally, and that would be C of X and Y and Z divided by the union of these two skew branches. Ideal associated to the union of these two branches. All I need to do is to write down ideals of the first branch. I'm going to call it branch 1, and the second branch. I'm going to call it branch 2. So let's write down those ideals. Ideal of branch 2. So ideal of branch 2 is the all functions that vanish on the y-axis. I need to guarantee that I can put an ideal of all things that vanish on the y-axis. Okay, anything that has x in it and has z in it vanishes on the x-axis. So this is ideal of branch 2. Okay, and then all functions that vanish on the first branch. Okay, so the first branch is along the x-axis. If it was the x-axis, I would put x, I would put like y and z, right? Y and z, but it's not like that. It's actually a height away from x-axis. So it's going to be anything that has y in it vanishes there because it's along the x-axis, and then it's z minus t. So this is the ideal of the second branch. Okay, so locally, the structure algebra of this picture is exactly this thing. And makes sense completely with our ideas, right? So this is our, let's call this curve C at the time t. Time is shrinking and the two branches are in the limit approaching each other, and CT is the given by ideals y equal to 0, z equal to t, union x equal to 0, and z equal to 0. This is the y-axis, and this is the other branch, branch 1. So this is exactly what we have over here. Okay. So no problem. This gives us O of z at the time t, O of zt. Okay, so let time pass. So I would like to see how the progression of O of zt is as time goes to 0. So as time goes to 0, in order to see that, I need to basically see what's going to happen to this ideal down here. Then I can basically immediately say what's going to happen to it. So O of zt, limit of it, is given by taking limit of ideal. Ideal y z minus t and times x and z as t goes to 0. So let's do that. So first, let us, we would like to calculate limit of this thing, this product. So what is this product equal to? So this product is an ideal. Product of ideals is an ideal. So if I multiply all the functions that are generated by these pieces there, let's just see, xy is there, right? And yz is there, right? And then x times z minus t is there, right? And then z times z minus t is also there. I'm taking the limit of this as t goes to 0. So if I do that, if I let t goes to 0, this would be ideal generated by xy, yz, x times z, and z squared. Because this goes to 0, right? Okay, so this is that ideal. So then limit t goes to 0 of O of zt locally is exactly C of xyz modulo xy, yz, xc, z squared. This is what module theoretically, the structure algebra of that curve on that particular affine patch will be. Now, compare this. I mean, you can see that, right? You can see that this is the limit as these two branches approach each other. You also agree by your eyes that locally, I could have just looked at outcome of this deformation process, which would be just the union of the x and y axis, right? As the two branches come together, this is what I'm seeing. So this is x-axis, y-axis, z-axis. Okay, but what would be then this one? It's the union of x and y. So ideal of this thing, if you didn't tell me that this is a limit of a deformation, ideal of this picture is all the functions that generate it. It's the union, this is union of x and y axes. That's it. Ideal of the union of x and y axis is x times y, generated by x times y, and z. So O of x-axis union y-axis is in fact C of x, y, z divided by x, y, and z. This is bizarre because if I take x, y, and z, I can expand it, right? So let us compare this ideal with this ideal over here. I'm going to put it in here. I'm going to write it in here. xy is there already, good. But then anything that gets multiplied by z is there. xz is there, yz is there, and z itself is there. Now compare. Well, xy and xy are both here. xz and xz are both here. Yz and yz are both here. But in one of them, there is the z, but in the other one, there is only z squared. Z squared is here. It's correct because z times z is z squared. But z is not an element of this ideal, because the smallest degree with z in it is 2. So as you can see, it seems that algebraic geometry suggests that there is a big difference between union of xy axis and the result of deformation of the two askew branches of this curve as t goes to 0. Instead of, if it is the result of the deformation, we get almost z, but a point of multiplicity 2, really. And that's exactly deformation or fattening of that origin in the z direction. We discussed about this thing. A point of higher multiplicity, nilpotent fattening, basically is a fatter object, and it deforms in the direction of the deformation. So if I really want to compare these two pictures, here I have locally these two branches approaching each other. This eventually gives me xy together with the fat point versus what we had before, which is just xy. These two pictures are not equal to each other. This fat point, this multiplicity 2, is exactly the embedded point that we are talking about. So if you'd replace your point of view from the space that parameterizes just curves to the space that parameterizes the structure sheaf or ideal sheaf of curves, you would be realizing that your curves can have embedded structure or reduced scheme structure. So the space is not exactly just the space of curves, but these embedded points. So this embedded point for us is that z square thing that we were just talking about. If you continue the deformation process, you can have z to the 3, z to the 4, and this point keeps going up and detaching from the curve. So what the Hilbert scheme parameterizes, it parameterizes not just curves, but curves with embedded points on them or off of them. Okay? And this is something that we need to worry about because Hilbert scheme is a moduli space. So it's the space co-representing a moduli functor. And we did see that the moduli functors allow us not to just study one object, but deformations of that object. So we should always worry about curves with embedded points on them. Okay, so let me write it down. These embedded points can be deformed off the curve. Hence, we see that the Hilbert scheme parameterizes non-pure. Not non-pure means it's not just naked curves. Non-pure means not only naked curves. Non-pure, one-dimensional subschemes in this case. Okay. So what we will see is that the good thing is that, as we will see, if you look at the structure sheaves or ideal sheaves, I mean, remember, you would think that maybe I should count the structure sheaf, but I say that you shouldn't. The structure sheaf has in the numerator just the polynomial ring on which this variety is defined, or this ambient scheme is defined. Here is P3. What gives you understanding of the structure sheaf is the ideal. So maybe you should just study ideals. So this ideal goes to O of X, and we have O of X modulo ideal of Z in X. And so the Hilbert scheme parameterizes the ideals. And the good thing about ideal is that you will see later that its automorphisms are going to be 1 over the moduli space that you're going to study. They're actually going to be infinite order automorphism C star, but stability forces you to see that the coarse moduli space underlying the Hilbert scheme will have only automorphism given by identity. So your hope is that when you calculate numbers over this moduli space, what you divide by, which captures the order of automorphism of ideal sheaves, is going to be number 1. So you will calculate integers. The only problem with this point of view is that still, as you can see, even Donaldson-Thomas theory is not what we were looking for, because you get something and you pay some price for it. You gain the fact that you have enumerative invariants, integer valued invariants, but with the price that you're not really counting curves still, you're counting curves with some reduced structure, some configurations of points on them and off them. Nevertheless, this is very important, and this has shed a lot of light on understanding of curve counting in ambient varieties. I must say certain things. Almost 100% of the knowledge that we have about Donaldson-Thomas theory is coming out of the result of Richard Thomas. He was the one who first successfully showed that these numbers are well-defined. And best source to learn about it is his papers. Even this example, I must say, there is a good memory I have. This example, which is very instructive, always for me was instructive, is the one that I remember he mentioned. I think there was some conference, and he was just giving us some point of view, like introduction to Donaldson-Thomas theory. And this exactly is the example that he mentioned. It was eye-opening for me. And that's why I never forget it. Each time I teach this course, I just use this very example, because that's it. You can suddenly see what's going on. So let us stop here, and then later I'm going to, like how we did it for Gromov-Witten theory, I look at the moduli space, deformation theory of ideal sheaves, and then calculations of invariants and some of the technicalities. Okay, let's stop here. Any questions? Okay, Enno, are you there still?
I am.
Okay, what do you think?
It's a pity that I missed the first lectures. That would have been interesting.
We come back to it. We come back to it. There is a big discussion on big quantum cohomology. There's a discussion on the small quantum cohomology. Then we do Donaldson-Thomas theory. Then we do big quantum cohomology. Then I hope really to discuss connections between Donaldson-Thomas and Gromov-Witten. That's the most important thing. We would like to show that ideal sheaves counting of curves is the same as counting of curves, but that's not easy at all. And it lies exactly in this difference that ideal sheaves see not only naked curves, but also points here and there. So you need to somehow make a comparison between somehow counting only the naked part of the curves out of Donaldson-Thomas invariance. In kind of, you want to just count the naked part, but it's very hard. You need to delete those points that can roam around. So, well, we will discuss it. It's beautiful machinery. This developed by others, really. Ponder, Nekrasov, Akunkov.
Did you do the construction of the moduli spaces?
I can do the construction, yeah.
No, I mean, did you do for the stable maps?
For stable maps, I have done, yes.
Okay, then I need to go back to your lectures.
Yeah, very thoroughly. If you look at the beginning of the lectures, you can actually see it. Yes, for stable maps, I've done.
And virtual fundamental class and so on.
We did that too. Yes, in the class. I was actually in person there, and yes.
Okay.
Okay. If no question, let us meet 1:15 Wednesday. Eastern time.
All right, then.
1:15. All right.
Yes.
Thank you, Mohammed. Thank you, guys. See you.